So yesterday when I was talking, I had just posted the things. And I think if you were here yesterday, you heard me say, I thought I had linked to this week's module, but I didn't hit save. And I went off to do yoga and I came back and I realized, oh, you didn't have access to that. So for a couple of reasons, I really expected no one yesterday to have seen the content yet, but I'm hoping that today you have, that you watched the videos. And this week, there's less content, but the content is it's getting a little more complicated. And that's why this week is a little bit lighter. There's really just two subjects. We're talking about covalent nomenclature, which I do want to talk about a little bit today. And we're talking about this idea of the mole. And so if you've seen the video, when I talk about this idea of the mole, it will make more sense. If you haven't seen the video, that's okay. And I'm really glad you're here. Just, keep breathing and don't feel anxious, and then watch the video and pieces will come together. There's no perfect order to do this in, and everybody has to put it into their own head, which requires just investing time in the content, which you're doing. You're here, so you're going to be fine. Okay, so I'm going to start with this idea of a mole. I never took high school chemistry because the guy jumped into the mole concept. I just remember thinking, what is a mole? I can't do this. I'm not smart enough. And I dropped the class. And then I came to college at Sierra and took Chem 1A, and I realized, oh, it's not that hard. I don't know why I was overwhelmed. Because it's just a group number. How many in a pair? 2. A pair of socks is 2 socks. A pair of gloves is 2 gloves. A pair of pants is 2 pant legs. How many in a dozen? 12, unless it's a baker's dozen. How many in a mole? Well, it's a really large number. So this idea called mole is just a grouping number of 6.022 times 10 to the 23 pieces. And typically those pieces, the pieces can truly be anything, but in a practical manner, those pieces we start with atoms. And we usually go next to molecules, which are just groups of atoms that are sharing electrons covalently bound. And then kind of the ionic idea of molecules is a formula unit. It's the unit we use to represent the formula. And, I wish there was an abbreviation for molecules, and there isn't. But for formula units, I say FU, which gets a chuckle, or maybe, I don't mean it rudely, but it sticks. And then the formula unit is the unit of an ionic compound that is made of ions. And so ions are other pieces. These are the pieces we typically talk about. Okay, so a mole is just a group of pieces. Why is it such a big number? 6.022, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. It's a huge number. Why so big? Because atoms are really small. Atoms are so small that it takes this many to make up an amount that we can weigh on a balance, and it's in the tens place. So why was a mole chosen? I don't know why the word mole was chosen. What was Avogadro thinking? But there's a bunch of jokes about avocado and guacamole, things like that. But it was chosen so that we could reuse the number on the periodic table that comes from the mass of an average atom. And so when we talk about things like, here's iron. Iron is element number 26. And there are different isotopes of iron, but when you mix them together and you find an average iron, which doesn't really exist, the average mass, the weighted average, is 55.85 AMU per atom. So one atom has that many atomic mass units. What is this strange thing? Well, an atomic mass unit is just a mass unit. Just like for measuring lengths, we might talk about kilometers or centimeters or miles or inches. There's a lot of length units. There's really only 2 mass units, and those are grams and AMU, and they're related. And AMU is equal to 1.66 times 10 to the negative 24 grams. That is not a number that you need to memorize. If you ever needed that number, here's how you get it. Using my calculator, I'm going to type in 6.022 EE23. So now I have a mole on my calculator. And then I hit my reciprocal key, which says either 1 over x or x to the negative 1. It's just a way of flipping it. So if I put in 2 and then my reciprocal key, it would give me 0.5. It would take this fraction, 2 over 1, and make it 1 over 2. Super powerful key. If you haven't learned to love that key, you will sometime this year. And when I do that, I hit my reciprocal key. Oh, look, there's that number, 1.66 times 10 to the negative 24. So you don't need to memorize it, and you can always find it because you do have to memorize what a mole is. Just know that atomic mass units are mass units, and so are grams. Pounds aren't really, they're force units, but we pretend that there is an equivalency between pounds and 1,000 grams, kilograms, because the force due to gravity, the acceleration due to gravity doesn't change much. To 3 sig figs, it's the same anywhere on the Earth, and we pretty much stay on the Earth all the time. So we pretend that pounds are a mass unit, sort of, but they're not. They're our mass being acted on by the acceleration of gravity. I digress. Let me go back to the point. So Avogadro wanted a grouping number like pair or dozen that would reuse that number, and that's where the mole came from. If you talk about a group that is this large and you put it on a balance, it has that many grams for a mole. So the whole idea was we can measure things in grams. We can't really count things. Atoms are too small. So a mole is a useful grouping number. We just need to learn how to use it. We just have to learn how to use it. And so that's the main goal for today, is to talk about how to use it. So a mole is just a group. Can you have a dozen pennies? Sure. Dozen doesn't always mean cookies. Can you have a dozen cats? Sure. That's your thing? So dozen just means 12. Mole just means 6.022 times 10 to the 23. So it doesn't matter what the mole is of. It works for everything. So if I want to go from pieces to mole, I divide by Avogadro's number. If I want to go from mole to pieces, I multiply by Avogadro's number. Oops. Do you have to memorize that? No, because you're good at unit conversions, and you'll do it the way that makes the units cancel and gives you the proper answer. Okay, so pieces to mole, mole to pieces, that works for everything exactly the same way. If you want to go from mole to mass, or from mass to mole, now you need a number on the periodic table. So now you're going to need a molar mass to get to grams, or you divide by that same molar mass to get back to moles. So this is like a roadmap that's going to be very important in our class. And honestly, this first part, using Avogadro's number to get from pieces to moles, we do it a lot in this chapter, and then it just sort of sprinkles throughout the semester. It doesn't happen a lot. Avogadro's number is important. It's really important this chapter, or at this time. But this other idea of how to go from a group to a mass is very important throughout chemistry. Every week we'll be using this idea. So a typical question for us just starting this week looks like, how many moles is 1.25 times 10 to the 25, and then pick a piece. I'm going to say copper atoms. And remember, atoms could really just be formula units, molecules, or ions. It can be any piece. So here we have extraneous information. It doesn't matter what kind of atoms they are. It's pieces, and we're going to put them in a group. So I start with the physical quantity, number plus units. And it doesn't matter if I say copper atoms or atoms copper. I need to have the unit atoms, and I need to be specific copper, because there'll be a point where we're using balanced equations to go from one kind of thing to another kind of thing. And we need to keep track of we have to be specific about our smallest unit. And now I use Avogadro's number, 6.022 times 10 to the 23 atoms of copper in a mole of copper. So sometimes students run into problems here because they're not using their calculators correctly. To do this, you want to say 1.25, either EE or EXP, whatever your calculator has, and then you put in the exponent, which is 25. And when you type it in this way, it is one number. And the calculator knows that. Does it matter at the beginning? Could you put times 10 to the 25? Sure, it wouldn't matter. But when you divide, it can lead to problems. So this next part, I'm now going to say divide by 6.022 EE 23. And then I hit equals. So we're dividing by one number in exponential notation. But the calculator understands that the 6.022 and the 10 to the 23, they are part of the same number. It's just a really big number. If you don't do that, and instead, let me get my red to say don't do this, it's wrong. If instead you said divide by 6.022 times 10 to the 23, then your calculator is going to see this part where you said times, and that means multiply, and it puts it in the numerator, and you end up with something like, 10 to the 48 for your answer, which is not right. So you need to use the exponent key. If you're getting really large exponents, 10 to the 48, 10 to the 47, 10 to the negative 46, really small exponents, then this is the problem. You're not using that key that you should be using. Okay, so let's all type it in using our calculators to make sure we can do this. I started with 3 sig figs, I divided by 4, the number ends there. I either round up or round to even, but either way I get 20.8 moles of copper. Oh, I thought it was Michelle that was saying that. Who was saying where it is on this calculator?
Oh, it's me, sorry. It's right next to the x squared. Select the comma.
Right here? Oh, here. Oh, it is a second function, comma. Okay, on your fancy calculator. Typically, you can't use this calculator in general chemistry, so that's not one I'm familiar with. But that's good to know. Okay, good. So that's just getting from pieces to the group. And now let's go the other direction. So if you had 3.2 moles of something, how about zinc atoms? And the question is how many atoms? So I'm starting with the given, number plus units, 3.2 mole zinc, and I'm giving complete units. Mole is the group and zinc is being specific. And now I'm going to go 6.022 times 10 to the 23 zinc atoms, state the piece, is a mole. Mole of what? Mole of zinc. 2 sig figs. The idea of Avogadro's number works between any kind of piece in the group. The group is called a mole. And now we're going to talk about specific elements. And so now we're going to need the molar mass off the periodic table. So here's, I don't know, how about gold? So the question might be, how many grams is some amount of moles? So start with the given. And now I'm going to use the relationship, which is and that number only works for gold. This time, let's start with grams and figure out how many moles that is. So what if we had, I don't know, 102 grams of gold, and the question was how many moles? Oops, that's not right, is it? It's 196, right? So here's our roadmap. I can go from pieces to moles to mass using Avogadro's number for the first step and then the molar mass for the second. Or I can go backwards using those same ideas. It's just whether I'm multiplying or dividing. So one of the kinds of pieces that we can have would be a molecule. And there's two kinds of molecule. One is a covalent compound and the other is an element. Some elements are polyatomic, and if they are, it's because they share electrons. So some of you are going to run into this on the practice quiz, which is why I gave you 5 practice quiz opportunities this week, and then a very different quiz. Like usually the practice quiz is the real quiz, but because there's question groups, I don't think you're going to get too many of the same questions. This time I made 2 separate quizzes because I want you to do it. This isn't a mistake I've already gotten emails about, so I know it's a common mistake, which is not a problem. It's just something we need to address. But if I said something like, how many bromine atoms are in 10.5 grams of bromine, you need to understand that bromine is a diatomic molecule, and bromine here means Br2. So my starting amount is 10.5 grams of an element that is a molecule. So when I find the molar mass, I have to go to the periodic table and find bromine. But understand that 2 bromines add up to make 1 molecule, so I'm gonna have to add those pieces together. My sig figs here are correct because if I add these 2 numbers, I can gain in the hundreds place. So now I have a molar mass that's good to 5 sig figs. But if you multiply by 2, it would be good to 4 sig figs. Okay.
Hey, Sue,
Yeah.
did you mean to write Avogadro's number on the bottom of between the pieces, mole and grams on the bottom? It says to use Avogadro's number twice? No. Okay.
No, you're right.
I just wanted to make sure that I was following. Thank you.
No, I appreciate you correcting that because somebody who's not paying attention will watch the video and be confused. So thank you for correcting me. I really do appreciate that. Okay, so I've gone from grams of bromine to moles of bromine, but what I have is a molecule, and the question said, how many bromine atoms? So 1 mole of this molecule, I'm looking at the formula here and seeing that it has 2 moles of atoms. And then I need to continue on and go from moles to pieces. Okay, so grams of the molecule canceled. Moles of the molecule canceled. Moles of atoms cancels, and we're left with just bromine atoms. Now I'd like to show you how somebody can set it up wrong and get the right answer, but that's not going to help them on the exam, where I'm going to need you to show me your work. So in this step here, where I had to double the molar mass, it's like on the top equation in blue, I'm dividing by 2. And then this step here, where I'm taking into account that bromine is Br2, I'm multiplying by 2. And so for that reason, the number still works out, but it's wrong because the thinking is wrong. The student needs to understand that bromine is a diatomic molecule, that Br doesn't exist. Br2 exists and Br minus 1 exists, but bromine by itself doesn't exist. Okay, that was an example of a molecule that was an element. Now I want to do a molecule that is a compound. So as soon as I say the word molecule, we're thinking covalent. Electrons are being shared. Nonmetals do that, and metalloids and nonmetals do that. Okay, so what if we said something like, I've got 7.2 times 10 to the 24 carbon dioxide molecules. And the question is, what mass? Big number. 526. Did you all get 526.1906?
Yes.
Grams. And then that won't work because I'm going to 2 sig figs. I can't say 530 grams because that's ambiguous. So I could go to kilograms or use scientific notation. Questions? Can I also warn you about another mistake students make sometimes? You know how units are super important? Like I need you to label with units. Units are worth points during the question and in the answer. Sometimes people will say 40.101 molar mass. And these are not units. That's a label. The units are grams per mole. So here I've said 44.01 I put the units grams per mole. I'm labeling it as molar mass, and then subscript, I'm telling you what it is the molar mass of. Okay, let's do something ionic. So ionic is going to be cation plus anion, and usually that's metal plus non-metal. It can be ammonium as a cation, and then there's no metals in it, but let's start with something like sodium sulfate. And what if we start with some grams of that and say how many sodium ions are present? So and I need the correct formula, because if I have the wrong formula, the next step, the molar mass, is going to be off. Nomenclature is super important. Okay, so I've gone from grams to moles. Now we need Avogadro's number to get to pieces. And now I need the formula, which tells me that there's 2 sodiums in every formula unit to get to the ions.
Wait, what does the FU stand for? Next to the 6.0
Formula unit?
formula unit. Cool.
Formula unit. It's the unit for a formula of an ionic compound. Okay, so 2 sig figs, round to the 10th place. It's going to round up. The answer is 4.0 times 10 to the 22 sodium ions. So earlier I said, I think this is a key that you're really going to love. I love my reciprocal key. And here's one example of where it comes in handy. So when I was sorting out the problem, you know, I had to figure out what the molar mass was for sodium sulfate, and it was on my calculator. And then when I started the problem, all I needed to do was flip this, and dividing by a number is the same as multiplying by its reciprocal. So then I multiplied by 4.7, and then I multiplied by Avogadro's number, and I continued. But if it's on my screen and I've already got all my digits there, hitting the reciprocal key allows me to just keep things on my screen and proceed with my problem. So if that makes sense to you, great. If it doesn't make sense, don't worry. But the reciprocal key is super powerful, especially when we have a lot of digits. And some people have, it's like, as I get older, a lot of things are going to pot. One of them is I'm starting to be a little dyslexic with numbers, and it surprises me because I was always very good with numbers. So I can't make that mistake if it's on my screen. Earlier, when we were doing the gold problem, I wrote down the molar mass for gold correctly, 196.97. But then I spoke it, I wrote it down here incorrectly, but it was on my calculator. And so I still got the right answer. I don't know if that's enough advertisement to support my idea. And I don't know if I've won anybody over, but just keep it in the back of your mind. Okay, so I think that I have addressed the mole and how to use the mole at a level that's appropriate for this week. Does anybody have any questions? If you're good with that, you can stay or go. It's up to you, of course. But I want to talk just a little bit about nomenclature, because covalent nomenclature is something that we've dipped our toes into, and it takes practice. So when we're naming compounds, we recognize something as a compound. because it has more than one capital and no charge showing. Is this a compound?
Yes.
Yes. Is this a compound? No. Only one capital. Is this a compound?
No.
No, it's an ion. So more than one capital, no charge showing. Is that a compound?
Yes.
Yes. Okay. So this is a covalent compound because it doesn't start with a metal. This is potassium. Potassium's a metal. That's an ionic compound. But I want to focus on covalent compounds. There are 4 kinds of covalent compounds. The first one are the ones that have common names. How many of those do we have in our class? Five. And here they are: water, ammonia, methane, phosphine, and hydrazine. If you came to Zoom yesterday or if you watched the video, hopefully you've made flashcards or you're already memorizing these formulas. Water's easy. Hope you see that one on the test. Ammonia. So ammonia should not be confused with ammonium. They're related, but they behave differently. Ammonium ion behaves as an acid, and ammonia behaves as a base. So even though they're related, they're very different. There's only 3 hydrogens. Sometimes I see crazy things like this, or this, but those don't exist. Okay, methane is lab gas. Phosphine is tweaker gas. Nitrogen and phosphorus are in the same column on the periodic table. And so it makes sense that if nitrogen combines with 3 hydrogens, that phosphorus might too. So these 2 are related for reasons that have to do with their valence shell, the outer shell electrons that are important in chemistry. And then hydrazine is rocket fuel. So think of ammonia like on steroids. N1H3, no, N2H4, one more. So those are common names that you need to recognize, and all of them have hydrogens. That should help. And then there's some that are hydrogen containing, not these, a different set. And how many of those are they? So hydrogen containing gases, there are 6. Hydrogen fluoride, hydrogen chloride, hydrogen bromide, hydrogen iodide. So all of those are hydrogen with a halogen, group 7. And then hydrogen sulfide, we don't say dihydrogen. And hydrogen cyanide, poisonous gas, smells like almonds. Okay, now there are some acids. Acids are very important. There are 3 kinds of acids. There's the kind where this was bubbled, one of these was bubbled through water. So HF with an AQ means aqueous, when bubbled through water. All of these came from ides, fluoride, chloride, bromide. They are all ides, and ides make hydroic acids. So all 6 of these can behave as acids when put in water, and when they do, they're hydroic acids. My ide has hydraulics. My ride has hydraulics. Anyway, something like that. There are 2 other kinds of gases that can, 2 other kinds of acids that cannot be called hydrogen something. They're just too bulky and they have oxygens. And those are the 8 acids and the ic acids. So if I pull off this hydrogen, I have nitrates, and 8s make ic acids. So that is nitric acid. For the other one, if I pull off the hydrogen, I have an ite. It's like the 8 nitrate, but 1 oxygen fewer. And ites make us acids. Ick. I ate a poisonous bite. So ick acids come from 8s. Poisonous acids come from ites. We would never call this acid hydrogen nitrate. That is not a name that it has. Only ides can be a hydrogen something. Okay, the fourth kind of compound is the one that students like naming the best. That's how many of each kind. Okay, so whoops. So if there's 2 nitrogens and 4 oxygens, it's dinitrogen tetroxide. If there's 1 phosphorus and 3 chlorides, it's phosphorus trichloride. So the first one we just name as the element, and then the second one we give the ide ending to. The first one, if there's only one, we don't say mono, but for the second one, we would say mono. So here's a good example of that. If I had OCl2, the first one is just, we don't use mono, even though there's only one, and we use the element name oxygen. And for the second one, we do use, if there's a 2, we would always say di. It's only mono that we drop for the first one. Di, but we don't say dichlorine because it's the second one, we say dichloride. But let's say that you saw it written this way, which I have seen. Now we would say dichlorine, use the elemental name, and we do use monoxide. So these are our 4 categories: common names, hydrogen-containing ides, gases, acids, and then how many of each kind use Greek prefixes. Questions? Okay, so now what I'd like to do is just put maybe 10 things on here and have you figure out either the formula or the name, and then we can talk through that. And again, this is totally optional. I mean, obviously, everything's optional. So stay if it helps you, but if it doesn't help you, you can go. Does anybody have questions on this page before I erase it?
Could I ask some questions?
Mm-hmm.
Okay, so for the acids, are we always trying to like cancel out the charges?
Right, because we're talking about compounds, and compounds are charge neutral.
Okay, and then so when we're naming them like oxygen dichloride, how would we know if it's like sulfite versus sulfur trioxide?
Sulfite, you could see the charge, or there would be a metal cation to cancel out the charge.
Okay.
Those are good questions. Okay, I'm going to erase this page now and just write a few things down. It's kind of a checkpoint. You're just checking to see if you know how to do this. So it is fine to try and get things wrong. Don't try to get things wrong. It is fine to try and to not be correct. But I just need to know if you've tried all 10. So as soon as you have, if you can just put in chat something like I'm ready, or did it, or got them, that would help me know when to put the answers down. And it doesn't matter if you're right, and it's not a contest. You can get there first. We're all learning. So to the 10 of you that are still here and trying, can I just tell you that you inspire me, and I really appreciate it. This is important, and you're staying to the end and checking your answers. And Sometimes I hear more from students that aren't doing the work than I get to see students that are. So it helps, it encourages me. Thank you. And we lost another one. So if you're ready, go ahead and let me know by typing in chat. Okay. The first one, we need to classify that. Is it an element or a compound? Compound.
Compound.
Is it ionic or covalent?
Ooh, covalent.
Covalent, because the first letter, P, stands for phosphorus. It's a non-metal. It's not a metal. Good. And then what kind of covalent compound is it? Common name, acid, hydrogen, or how many of each kind? Here's a hint.
Of each kind?
Yes, because it has no hydrogens. Hydrogens are the ones that fall into those other categories. So this is diphosphorus, and spelling counts, PHOS, PHORUS, unless you have a UK passport. Pentoxide. If you're
So
not
if I wrote pentaoxide, I would get that wrong on a test.
no, that one actually is forgivable. Pentaoxide. I let that one go. So if it ends, the prefix ends in an A or an O. But Courtney, once I explain this, you're never going to miss that again. And if the root word starts with an A or an O, we drop the prefixes vowel. But we don't do that when it's an I and an I. Triiodide is a thing. I don't know why. So I wouldn't take that point off. That's not a problem. Okay, the next one. Is it an element or compound?
Compound.
Ionic or covalent? Thanks for playing along, AJ. I appreciate it.
Covalent.
Yeah, how'd you know that?
Because you just told us.
And he was right. Good. So it's covalent, and it has hydrogens. So it's probably not a how many of each kind. Can't be. What is it? Acids start with hydrogen, and hydrogen-containing compounds start with hydrogen. So this is a common name. And what's the name? Okay, the next one. Is that a element or compound?
Element.
What's the name of that element?
Iodide.
Iodine.
Iodine. Yeah.
Iodine. Yep. Okay, AlCl3. What is that?
Chloride.
An ionic
Compound.
Yeah, it's a compound. It's an ionic compound, and it is aluminum chloride. Should I say aluminum trichloride?
No.
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 The next one.
Boron chloride. No.
Boron tetrafluoride.
No and no, but you're getting close. What is 3?
Oh.
Try. Boron is a metalloid, so it's going to be covalent, not ionic. And there's 3 fluorides, so it's trifluoride. And fluoride is spelled with a UO. And spelling counts. Boron trifluoride. Okay, methane. That's a common name. What's the formula?
I have a question real quick, if you don't mind.
No, I don't.
When do you use the tris and the dis and the pent? Because you didn't do it with like aluminum chloride.
Right, because aluminum is a metal, and so this is an ionic compound. That's why I
So you
didn't. But boron is a metalloid, so this is covalent, and that's why we did.
So do you only do it when it's a metalloid?
Or it could be a nonmetal. So this is also covalent. And so that would be carbon tetrafluoride. So if it's ionic, it typically is a metal and a nonmetal, except for ammonium, that's the exception. And if it's ionic, we never use those I can't say never. We do use those prefixes only this time. when we have this ion, so let's say I added a sodium to that to make an ionic compound. Let me hide those charges. That would be sodium dihydrogen phosphate. So dihydrogen is the one time when it's ionic that we do use a di. Typically, if it's ionic, we never use prefixes. Oh, there is one more. Sorry, dichromate. Chemistry can be frustrating. So let me add some sodiums to neutralize that -2 charge. This is sodium dichromate. So those are the only times if it's ionic, but it's part of this covalent ion, we use the di. Sorry, AJ, that probably wasn't helpful, but it is true.
Yeah, still super confusing. So you use the di and penta for phosphorus and oxygen, which are nonmetals.
Mm-hmm.
So diphosphorus pentoxide, right?
Right.
And then barium trifluoride metalloids.
Right.
So I don't
So
know,
if I have a metal plus a nonmetal, that's ionic. Don't use the prefixes. If I have a nonmetal plus a nonmetal,
okay.
That's covalent. You probably use the prefixes, but not if there's hydrogen. And then a metalloid is going to behave like a nonmetal. And this helps. That's covalent. And this helps. If there is a metal to make it ionic, it always is stated first. So a metal isn't going to sneak up behind you and be at the end of the compound.
Okay.
Yeah. Okay, so methane. Cows make methane, CH4. We don't call that carbon tetrahydride. That would be wrong. It has a common name, and that is its only name. Sulfur is an element, but it's one of those polyatomic elements. There are four old Superman. When you take the quiz and the practice quiz, if your molar mass is off because you forgot they were polyatomic, that's the problem. Okay, phosphoric acid. So I know it's an acid because it's in the name. And ic acids come from 8. So what is the formula for phosphate?
CO4?
3 minus. So that means I need to add 3 hydrogen ions to make something neutral. That is phosphoric acid. Hydrogen sulfide. So this is one of the 6 that is a gas. And sulfide would be 2 minus. So to make that a compound, we needed 2 H's. But we don't say dihydrogen, we just say hydrogen sulfide. It's the 3rd nonmetal category tonight, which I called hydrogen-containing gases. Okay, and the last one is ionic. Why? Because barium is a metal. It was stated first, and which is where metals would be. And +2 - 3, let's shoot for 6. There you go. Okay, so I know at first this isn't pleasant. Eventually it'll be a puzzle and it might be fun. But maybe not everybody's there yet, but it does take practice, so it's good to do. Tomorrow morning I have a Zoom at 9. Does anybody have a suggestion for what I should go over?
Not regarding a suggestion. I had a quick question before you.
Oh, yeah.
Answer. So with the last one that you just had, the phosphate, because obviously you need 3 of the barium to balance out the phosphate charge. How do you know, I think you were saying this yesterday, but how do you know when the subscript equals quantity or charge? Or sorry, quantity, I think you were saying about the subscript being quantity.
Oh, yeah, so I think, well, it's always quantity, but there's 2 kinds of quantity that we could be looking at. And one is, this 3 is saying 3 of these ions. This 2 is saying 2 of these ions. So those are the same, right? But for phosphate, PO4 3 minus, this 4 is just part of the chunk that has 3 extra electrons. So that 4 subscript doesn't break apart. So right now we're taking this idea of cations plus anions. Let's make the formula. But in 2 weeks, we're going to say, well, if I put this in water, is it soluble? Because if it's soluble, it's going to break into ions. How many ions? 3 plus 2 is 5. So when we get to that place, we need to recognize that this 4 doesn't mean these 4 oxygens fall off the phosphorus, because this chunk is covalent. Phosphorus plus oxygen makes it covalent. The things that fall apart are the cations and the anions. Did that answer your question, Marilyn?
It did. Thank you. It did. Thank you so much.
Yeah.
I have
Okay.
a quick question.
Yeah.
How do you know that you get 3 hydrogens on the phosphoric acid?
I needed to neutralize the -3 charge.
Oh, okay.
Because
That makes a perfect
compounds
sense.
Okay, good.
Yeah.
I also
Other
have a
question? Sure.
So for sulfur, if it says sulfur 8, how did you know there's going to be 8 sulfur?
Oh, because in a different video and on Zoom, I talked about the 3 polyatomic elements. These are them. And at the same time, I was talking about the diatomic elements, and I made a list like this. Horses need, oops, what am I doing there? Horses need oats for clear brown eyes. So this is a list of diatomic elements, and this is a list of polyatomic elements. You just have to know those are the kinds of allotropes that are stable that we're going to use in our class. Allotrope is just a fancy word to say, well, oxygen could be O2 or it could be O3. And it turns out there's actually a kind of oxygen that is a blue liquid that's O4, but not at this pressure. Anyway, these are the ways that oxygen, the element, can be stable. Carbon has allotropes that we're familiar with. Like there could be carbon that is a diamond. It's my favorite allotrope. And then there's carbon that's graphite. So there's different ways that the element can exist. For us in our class, for phosphorus and sulfur, those are the ways we're just going to have to learn they are. Is it the only way they can be? No.
Cool.
But it's very common.
What was your saying for the POS again? The P403?
Coral Superman?
Oh, thank you.
Yeah, because Superman has 8 letters.
Yeah.
Yeah. And this O is called ozone, and this one is called O2, but they're both oxygen. Okay. So tomorrow, I think maybe I'll do more nomenclature, unless somebody shows up and says they want to work on Avogadro's number.
Yeah, I think I could use some help in nomenclatures. That's me.
Me too.
No,
Me too.
That is everyone. That is
This
not
sounds
just
hard. I'm so stumped.
But you know what, in a week, so I have watched thousands, literally thousands of students learn nomenclature. You're going to be fine. I am not even worried about you. It's just work.
That's good to hear.
Yeah. But I know that panicky feeling when you feel like you're about to drown. Like,
Yeah.
Please tell me there's no more rules.
Because I'm stressed. I'm on page like 24 of the practice packet, and I'm like, you got like periodic on one of them. I'm like, how in the world did you get periodic? I think it's periodic acid.
It is.
I was like, what?
I would say periodic. Yeah.
Okay, there we go. It's
a real
periodic. I was like, what
It
is
does.
this?
It's only an acid at intervals, periodically. Yeah. But it does get easier. And this is a place where some students aren't going to put in the work. So please understand that I've been doing this for a long time. And I know there are 2 assignments this week that are worth points. And I know that the students are going to lose points because that always happens. But I tend to have a lot of A's at the end of my class because we don't need to panic over any points. We just have to not lose the same point again and again, you know? So please trust that I don't we're not going to have a 100-point quiz on this tomorrow. I know it takes time. But
Good
it
to
can
know.
be done. It can be done. The students just need to apply themselves. So.
All right.
And you're the people who are here at 8:10. So like I said, I believe that you are the hard workers and you're going to do what you need to do and you'll learn it and you'll be fine.
Cross our
Okay.
fingers.
So if anybody has different questions, like we are done, but I'm still here. So feel free to stay on. I'm going to stop screen sharing. And then ask your questions and I will answer them.
Okay, I just want to tell AJ that I was kind of like extremely confused. So I literally went over every single meeting that was recorded from last week. I watched every single one of them again, and it helped a lot. It took away a lot of that confusion. So I'm probably gonna do that again this week. But I felt the same way that you do.
Sense.
I felt the same way you do right now, and that's what I did, and it helped. So maybe that might help.
Cool.
I think
All right,
Courtney
thank you.
told me privately that she thought these were fun. Didn't
They
you?
are fun. They're fun. Yes, they're fun now that I'm trying, starting to understand it.
Yeah.
Doesn't mean I'm not getting some wrong though.
No, and that's fine.
Yeah, the ones I can do are pretty fun.
Yeah. They're like a puzzle, right?
Yeah,
They're like a
they're
puzzle.
brain pieces for sure. All right.
All right.
So
Thank you very much.
you're welcome. Here's some
Yeah.
encouragement is you'll need this in 3B and in 1B. Like it doesn't go away.
Oh,
So
God.
the
It'll
work
be
up
useful.
front will save you pain later.
Thank you so
Hopefully.
much, Sue. Have a good night.
Thank
You
you.
too.
Bye.
Bye. Have a great night.
You too.